Alright, so hello everyone. This is the solution video for the Edexcel June 2018 S1 paper. Alright, so first question, a random sample of 10 cars. Now this 10 is going to be our value of the total number of items of different makes and sizes is taken, and the published miles per gallon P and the actual miles per gallon M are recorded. The data are coded using variables x equals p by 10 and y equals m minus 25. So these are two codings that are applied to the collected data. All right. The results for the coded data. Okay, this is the table for the coded data x and y are summarized below. Okay, so we have, as expected, 10 sets of data here in 10 columns here for 10 corresponding values of x and y. All right. You may use, okay, so here are a couple of summary statistics given here. Okay. Question A, part A, show that the summary statistic of y is equal to 626.025. Okay. So here, as we can see, the formula for the summary statistic of y is equal to the sum of y squared, the sum of if you square every value of y and then you take your sum, minus from that you subtract the square of the sum of y, the square of the sum of y divided by n, divided by n. All right. So this is the formula, and here I've just found a couple of values for, and these are not given here. That's why we have to find them manually here. So sum of x and sum of y. Okay, basically, sum of x is just the sum of all the x values. Sum of y is just the sum of all the y values. So here what we need is actually the sum of y. We'll see where we need sum of x a bit later. Uh, and we are also given, this is given the sum of y squared. So we have all the values that we need, and n is 10 as I mentioned before. So we'll just plug all those values in for sum of y squared, sum of y, and n, and we should get our final answer, and that is exactly 626.025 as expected, because it was show that question. So we have indeed proven that. All right, next part. Find the product moment correlation coefficient between x and y. Okay, so it's basically written as R, and the formula for that is your mixed summary statistic. So this is how I like to remember the formula. Basically, your mixed summary statistic, the one that involves both the independent variable, both the variables, divided by the square root of, you have the product of your pure summary statistics, you could say. So s of double x and s sub double y. So that's how I like to remember it. And the square root, I could call this thing, the square root of the product of two things, you could call it their geometric mean. So that's how I like to remember this. Now let's move on, and here we need some of the information that we previously saw. That, so this is just for reference. Now if you use the formula, what do we have? We have all the information that we need. Well, we have s sub xy, we have s sub double x, and do we have s sub double y? We actually found that in part A, right? So we found this in part A. So we'll just plug all the values in, as you can see here, and we'll get a final answer of 0.981. We'll keep it to 3 significant figures. All right. Give a reason to support fitting a regression model of the form y equals a plus bx to these data. All right. So as you can see, our product moment correlation coefficient R, the value of that is 0.981, and that is very close to 1. Okay. So whenever the absolute value of R is very close to 1, okay, very close to 1, or you could say if R is very close to either -1 or 1, when these conditions are met, when either or whether if either of these conditions are met, basically these were equivalent, really. Being close to -1 or being close to 1 really just means the absolute value being close to 1. or just the magnitude or size, you could say. So basically, when the size, the pure value, the positive value of r, it's close to 1, we actually have a very strong correlation. Okay, and here it's actually very, very strong because it's almost 1. It's almost 1. So that's why we have a strong correlation, and in particular here it's positive because the value of r, as you can see, it's positive. But what matters most here is that it's a strong correlation between x and y. That's why this supports a linear regression model. Okay, so this supports a linear regression model, and in the form y equals a plus x. All right. So part D, find the equation of the regression line of y on x. Y on x. So this is important. We'll come back to this in a bit. Giving your answer in the form y equals a plus bx. Give the value of a and the value of b to three significant figures. So they mentioned the accuracy here. So we need to follow that. All right. First thing here in this formula, what is the value of b? The formula for that is b is equal to s sub xy divided by s sub xx double x. The way I remember this is b is equal to your mixed summary statistic divided by, and here is the key thing. It's going to be one of your pure summary statistics, but which one? Do you take double y or double x here? And the answer to that is it's going to be your independent variable. Now there, you could find this information from quite a few places. Okay, one thing is they said y on x. So on what? That variable is going to be here. Okay, another way to find that is, in this equation, what is the variable next to the b? What is the variable adjacent to the b together with the b? That's another way to find. So here it's going to be x. It's going to be double x because that's the independent variable. Okay, and we are also going to need some of the information here. So that's for reference. Now we have s sub xy, we have s sub xx, double x. So we should be able to find the value of that came in the wrong order, I think. Okay, so we should be able to find the value of b, and it comes out to be 8.06 with three significant figures. All right. Moving on. Now we need to find the value of a, and the formula for that is a is going to be equal to the mean of y, basically the mean of your dependent variable, the other one basically, minus b multiplied by the mean of your independent variable. Okay, and there's another way to remember this. It's the fact that your regression line must pass through the point x bar comma y bar. So here's how you can find the formula for f if you find this too difficult to memorize, or if you forget it. So this is definitely the equation of your regression line. This is what you're hoping to find. So we have y equals a plus bx, and as I've said, by definition the regression line must pass through this point x bar comma y bar. So if it does pass through that point, then if we plug in these values for x and y, we should still get a valid result. So y bar, this point will satisfy this equation. Okay. So for in place of y, you have y bar, so y equals y bar, a plus, and now here x is x bar. Now from here, we know every other value is known, so we can find a. A is going to be y bar minus b into x bar, which is basically what we have here. So this is one way you could find the formula for a in any situation. Really, just b, you need to keep it in your head because it's not given in the formula sheet, your formula booklet, and you cannot actually find it that easily either. All right, so moving on to the calculation of a. Now we actually need the mean of y and the mean of x here. So I've calculated them. As I've said, we would actually need the sum of x, and this for this part. So using the sum of x and the sum of y, I found the mean of x and the mean of y, and I just plugged them in here. We also have b from before, and all of that gives us the value of a, which is negative 25.4. All that we need to do now is they told us to find the equation of the regression line. So just need to plug the values of a and b into the equation, and doing that we get y equals negative 25.4 plus 8.06x. All right. Let's move to the next part. A car's published miles per gallon is 44. All right. So as given earlier in the context or prose of the question, the published miles per gallon is basically P. So the value of P is 44. Estimate the actual miles per gallon for this particular car. And also as given before, the actual miles per gallon basically refers to M. So what this question is saying is, given that P equals 44, find M. All right. So if p is now here's actually the problem here. We our regression line from the previous part, and all that we've been dealing with so far is actually all concerned with x and y, not p and m. So to solve this problem, we'd actually need to reverse our codings that we did before. X and y are just coded variables for p and m respectively, so we need to backtrack here. All right. So first, what I'm going to do is, we have the value of p and x equals p by 10. From here, what I'm going to do is find the value of x. So I'll just put 44 here, and you get the value of x equals 4.4. Now, with this, I have x, and I have that equation, right? I have that regression line equation between x and y. So from here, I'll find y first. So for x equals 4.4, I'll first find y, and it gives me approximately 10.086. Now I also have that the coding equation between y and m. It's y equals m minus 25, and from here what I can do, y is equal to this, y is equal to this, basically means what? M minus 25, the same thing, m minus 25 is equal to 10.086. And now from here I can find the value of m, that is 35.1 to 3 significant figures. All right. Now, part F, comment on the reliability of your estimate in part E. Give a reason for your answer. All right. So we need to comment on the reliability. Okay. One thing that we can see here, this is the most important thing actually. I'll bring out the table here for reference. Now, when is an estimate reliable? When is an estimate reliable? When you have, suppose say a set of data, suppose say it's like this, you have a bunch of points, and you can I should draw them a bit darker here. So you can basically find a line of best fit. Okay, suppose say this is as much as your point square. You can find a line of best fit as we have found here. Okay, but the thing is, suppose say our points begin here and end about here. Okay, so if you use the regression line to find any value, any value of the dependent or independent variable based on the other, within this range, this is basically the range of the data. This is basically the range of the data. Within this range, if you use the line to find any value, to estimate any value, that is going to be reliable. This is called interpolation, where you're using, you're estimating within the range of the data. But if suppose say you want to go a bit ahead, more than the data, or even a bit backwards, suppose say, okay, and here and here and here, you would be actually outside the range of your data. If you can still use you can still actually forcefully use your regression line equation to find the values here, but there is really no guarantee that they'd be correct. The data doesn't give any guarantees for those estimates. Okay, because it's not included there. So that's why this is called extrapolating. It's called extrapolation, and it's not reliable. All right, so it's generally not recommended. Okay, so here what we need to actually see is, are we interpolating or are we extrapolating? So here p equals 44, it's equivalent to x being equal to 4.4, as we have found. So in this table between x and y, you can see that the range of x, it goes from 3.65 to 6.89. and the way you can find this is 3.65. Let's see here. This is your lowest value. There is no value of x lower than this, and this is your highest value. There is no value of x higher than this. So this is your range, 3.65 to 6.89. Now, does our value of x, which we used to find this estimate, is that within this range? Well, yes, 4.4 is indeed within this range. Okay, so we are actually interpolating, we are not extrapolating, and thus our estimate is reliable. Our estimate for m is reliable. All right. Now, question number 2. Two youth clubs, East U and West U, decided to raise money for charity by running a 5-kilometer race. All the members of the youth clubs took part, and the time in minutes taken for each club to run the 5 kilometers are recorded. The times for the West U members are summarized in figure 1. Yes, so this is a box and whisker plot, basically for the West U members. All right. Now, what is our question? Actually, that came out a bit early. Write down the time that is exceeded by 75% of West U members. Okay. Now, by definition, now this is something that is very important for the whole part of this question. Suppose say you have a data set, so I'll just represent that as a bar. Okay, I'll just represent that as a bar. What are basically the quartiles? What are basically the quartiles? The quartiles are just some values that divide your data by 25%, so 1/4. That's why actually they're called quartiles. Okay, they divide your data by 1/4. So first comes your first quartile, as should be obvious, and below this you have 25%. Below this you have 25%. Actually, I'll cover the rest in the next part, so because that's needed there. But yes, the first comes the lower quartile. It exactly it divides the data here. From the beginning up to Q1, you have 25% of your data. 25% of your data is in this range. All right. So the question is, write down the time that is exceeded by 75%. So isn't this the upper 75%? Okay, isn't this the upper 75% of the data? So this upper 75% exceeds which value or which time? Basically this one, right? Q1. So by definition, Q1, the lower quartile, is the time that is exceeded by 75% of the members, or 75% of the data. So all that we need to do is find the value of the lower quartile. Here I've already marked the values of all the quartiles, actually Q1, Q2, and Q3. So Q1, and the in a box and whisker plot like here, the quartiles are given by these long lines. Okay, these long 3 lines in the middle, and they're in order. So Q1 is going to be the first one, as you can see, it's 29. Q2 is going to be the second one, and it's exactly 32. And Q3 is going to be the third one, and it's 33. It's right in the middle here. All right. So what we need is actually Q1 here. This for reference later. So Q1 is actually equal to 29 minutes. All right. Let's move on. Times for the EastU members are summarized by the stem and leaf diagram below. Okay, so you have the diagram here. Find the value of the median and the interquartile range for the EastU members. Now, this is for the EastU members, the stem and leaf diagram. All right. Now, here, one thing that we really need to be careful about is actually the key, and it's going to be given in the question. Now, we always need to keep this in mind whenever you take values from a stem and leaf diagram. Like this 4 here doesn't actually mean 4, okay, or this 9 here wouldn't actually mean 9. So 2 bar 0, it basically means if you have 2 on the left side and 0 on the right side, okay, these all of these every value on the right side are actually individual data points, but you cannot just read them by themselves. You need to read it together with the stem. Okay, so 2, if you have 2 here and if you have 0 here, if you're reading this data point, you first read the stem, so it's 2, and then you have 0, and then you have 0. This data point is 0, but what that actually means is 20, and this is going to be given in the stem what that would mean. This is 20. This is not 0, or this is not 2 either. This is 20. All right, so that's what we need to keep in mind. Okay, so one thing I've written here is the total number of data points here. It's 30. There are 30 members in total, and 30 timings for them. All right. So how do we find the actually, I should have mentioned what we were going to do. What's our target? Median, that's basically Q2, or second quartile Q2, and interquartile range. This is basically Q3 minus Q1, the difference between the upper quartile and the lower quartile. For that, we first need to find Q3 and Q1. Okay, so our goal is going to be finding every quartile. Okay, one of them is going to be our median, so that's one of the answers, and the other, the interquartile range, is going to be the difference between Q3 and Q1. So let's proceed. Okay, first I'll find Q1. I'll go in order here. So 1 by 4 into 30 equals 7.5. Okay, so why did I do this? Okay, what's the purpose of these terms? One thing is the position of every quartile. How do you find that? First, you take your total number of items. Okay, you take your total number of items and you multiply it accordingly. Now, what do I mean by accordingly? What should you really multiply by? And this all relies on the definitions of the quartiles, as I was showing, previously. So as I've already said, Q1 is at the 25% mark here. Q1 is the 25% mark, or at the 1/4 mark here, you could say. Q2 is actually again another 1 by 4th, another 1/4 to ahead of Q1. Q2 is here 1/4, and again another 1/4. So that's 2/4. Okay, and then again another 1/4 ahead, another 1/4 of the data, of the portion of the data ahead. You have your Q3. Okay, so it's all also divided. This portion is also 1/4, and the rest is just between Q3 and the very highest value. So this is what I was trying to say, how your quartiles divide the whole data in 4 equal portions, in 1/4, in 1/4 portions. All right, so how does this relate to here? So the way you find the position of every quartile is you take your total number of items, okay, and then you multiply by essentially how much, from the starting, how much does that particular quartile cover. Okay, so Q1, the first quartile, covers up to 1/4, right? 1/4. That's why you're multiplying 1/4 with 30, and we're getting 7.5. Now, since this is a decimal, since this is not a whole number, we're actually going to have to round that to the nearest value that's greater than that. So the I guess you could say the lowest integer that's above this value. All right, so if that makes sense. Now that is going to be okay. Actually, I could have stated that a bit more simple. Basically you round up. I don't know why that phrasing didn't come to my mind. Now yes, now this is going to give us Q1. As we can see here, all that we need to do is, eighth time, we need to find the eighth value here. So 1, 2, 3, 4, then you move to the next row, 5, 6, 7, 8. This is the eighth value. Again, we need to be careful about how we read this. So if we are trying to read this data point, we need to read it together with the stem. So 2 bar 8, that means 28 according to this key. That's why that's our answer here is 28. Now moving on to finding Q2, basically the median. Again, 30, your total number of items, that's actually not going to change, multiplied by how much does that quartile cover your data up, from the beginning, from the starting line. Okay, the starting point. So it's 1/4 and again another 1/4. So it's 2/4 basically. And this is another way to actually remember this. It's basically going to be something divided by 4. That something is actually going to be the number, the subscript of these quartiles. Okay, so here you have 1, you place a 1 here. Here you have a 2, you place a 2 here. Okay, and as you'll see, with Q3, it's the same thing. So so it's 15. So the value we get for the position is 15. Okay, now this is the slightly trickier case where you have a whole number for the position. We might think that it's just going to be, so if we try to find the 15th one, it's going to be, let's see here. Okay, so this is actually the 15th value. We might think that this is this is the median, this is the second quartile, but it's actually not. When you have a whole number, you take that, that position, you take one above that, so the 15th one, also the 16th one, you take the values at those positions, and then you take the average, you take their average. All right, so here what are these values? It's 3 bar 0, and this one is also 3 bar 0. Both of them are 30. Okay, both of them are 30. 30 plus 30 divided by 2, that's the mean, and then you get 30 minutes, and this is one of our answers, median. So half of the question is done. Now here, same method, I found q3. You have a 3 here, you place a 3 here. You could also think about this, up from the start to q3 of 3/4 of your data in total. Now this is going to be 22.5, the position value, and well, if it's again a decimal, so we need to round up, so it's 23rd timing. From the diagram here, from the stem and leaf diagram here, this is the 23rd value. You can count up, from the start up to here. So, and this is 3 bar 2, basically going to be 32. Okay, so the value is 32. Now we are not done yet. We found the median, but our target actually wasn't the other quartiles. It's the interquartile range, but the value for the formula for IQR is Q3, your upper quartile minus your lower quartile, Q1. That's, as we can find here, 32 minus 28. That's basically 4 minutes. Okay, so let's move on. Okay, so an outlier is a value that falls either more than 1.5 multiplied by q3 minus q1. It's basically your interquartile range. So I'll write that. That's IQR. Okay, above q3. So it's going to be exceed, so plus, and then more than. I was a bit confused with more, but it's more than this value below q1, below q1. All right. So an outlier is any value that is either more than this value that we're going to get, or less than this value that we're going to get. So in one way you could say that this is your upper limit. Okay, any value that's more than this upper limit is going to be an outlier, and this is likewise your lower limit. Any value that's going to be lower than this value that we're going to get is going to be you're also going to be an outlier. So this is what we've done here. So the upper bound, okay, for the outliers is now here is the most important thing, is actually interpreting what's being said here. So more than, okay, so I'll ignore this part because I've already discussed being more or less than that. But what's this value indicating? 1.5 into basically the IQR, Q3 minus Q1, above Q3. So basically Q3 and plus this more. Okay, so this is what I've done here, Q3 plus this value right here. Okay, and if you calculate this, what we get here is 38. Okay, using all the values that we previously found in the previous part. And same thing, actually before that, okay, so we have our upper bound. Is any value more than that? Well, yes, there is one value more than that. 3 bar 9, 39. That's more than that. Let's also check the previous value. It's 3 bar 7. That's 37. No, that's still below. So that's not going to be an outlier. Only one, kind of like the extreme upper outlier, you could say. Yeah, only one like very large outlier. That's 39. That's 39. Okay. Next, we're going to find the lower bound. So same thing, that almost the same thing we need to do here. First, we need to interpret what this value means. So basically, this portion below Q1, so basically minus. So Q1 minus this value right here. So that's going to be a lower bound. And if you use the plug in all our values, it's going to be 22. Is any value in this diagram lower than that? Well, yes, you have one. 2 bar 0, that's 20. That's actually less than 20. Let's also check the value next to that. That's 2 bar 2. That's 22. That's exactly 22. That's actually still not an outlier, because they've said that only when we go below this value, okay, only when we strictly go below or less than this value is it going to be an outlier. So even if you're on this value exactly, okay, then it's still not an outlier. All right, but actually, finding the outliers is not exactly the goal here. Well, we do need to, but what they're asking us is we're going to have a grid that's on the next page, and we need to draw the box plot for the EastU members. And now this is our box plot for these two members. Now, all that we here, I'll explain how we exactly got this. So, first thing is your quartiles, the quartiles that we previously found, 28, Q1 is 28, Q2 is 30, Q3 is 32. We found these before. These are going to be in order, these three long lines, as I've discussed before. Then you have just your box surrounding these, just containing or surrounding these. So, and then you also have your outliers. You'll just quickly mark our outliers. One was 39, another was 20, as we saw. The tricky part comes here. Where are your whiskers going to be, upper and lower whisker? There's some contradiction, or some confusion or controversy, you could say there. Often we'd like to think, okay, so is this, are these going to be our upper and lower bounds that we found before, or is it going to be something else? Well, here what I've done is, and this is, I believe, whenever you can, this is actually the safer option. You'd definitely always get your marks if you do this. Now, if you have your, we had our outliers, right? We had our outliers 20, and remember what I discussed. The value just next to that, it's going to, the next value, basically 20, it was 22. 22 is basically the lowest value, the lowest number that's not an outlier, right? Okay, and same thing here, our outlier was 39. The value next to that was 37, right? 37 is basically the highest value that's not an outlier, and these are actually going to be our upper and lower whiskers accordingly. So this is the lower one and this is the upper one. So we'll draw them like that. Just need to be a bit careful here is the length of the this portion right here. It's going to be less than the one, the lines that we use for the quarters, just a bit less. So that would be enough. All right, and then we just draw these whisker portions. So that settles the box plot. All right. Now state the skewness of each distribution. Part D. Give reasons for your answers. Remember that we have two distributions, actually, two sets of data, one for East U members, one for West U members. So we'll analyze them using all the values that we have found so far. And basically, I'll already say this skewness, okay, and especially where in this question where you have found all the quartiles, determining skewness is just going to be comparing two particular values, q3 minus q2, comparing this value with q2 minus q1. So let's see how that works out. So for the West U members, q3 minus q2 is 1, 33 minus 32, and q2 minus q1 is 32 minus 29 equals 3. Okay, again, I'm just using all the values here that I've already found. Okay. Now, all that we need to do is compare q3 minus q2 with q2 minus q1, and the rule is, if q3 minus q2 is greater than q2 minus q1, okay, it's going to be positively skewed. If it's less, it's going to be negatively skewed. If these two are equal, it's going to be symmetrical. All right. Now, what happens here? Q3 minus Q2 is actually less than Q2 minus Q1. Obviously, because 1 is less than 3. Okay. And now, that means that the data is negatively skewed. What happens for West U members? East U members? Q3 minus Q2. For them, we need to remember that the quartile values are different for these sets of data. This one we found right at part A, okay, and we didn't discuss that anymore. Okay, all these quartile values, and this is, the East U members are what we have been dealing with most of the time. So Q3 minus Q2 is 30 minus 32, as we just saw a while ago. That is 2, and Q2 minus Q1 is 30 minus 28, and that's also 2. Okay, so the values, these two values, q3 minus q2 and q2 minus q1, they're equal. That's why this distribution or data set is symmetrical. All right. Now, And that is the end for question 2. We'll move on to question 3. A manufacturer of electric generators buys engines for its generators from 3 companies, R, S, and T. Company R supplies 40% of the engines. If you want to express that, as a proportional decimal, it's going to be 0.4. Company S supplies 25%. Again, that's going to be 0.25, and the rest of the engines is supplied by company T. That's the rest. Basically, the whole proportion is going to be 1, same as in probability, and from that you subtract all the other ones. So minus zero point 0.4, minus zero point 0.5, and the portion for T is going to be 0.35. You can see here. Now, it is known that 2% of the engines supplied by company R are faulty. So I'll highlight that here. 0.02 as a proportion or probability, you could say. Uh, okay, so they're supplied by company R, and 2% supplied by company R are faulty. Okay, 2% of their supply is faulty. 1% of the supply of company S is faulty, and 2% of the supply of company T is faulty. Right? And 2% of the engine supplied by company T are faulty. All right. And an engine is chosen at random. Part A asks us to draw a tree diagram to show all the possible outcomes and the associated probability. Now, this is pretty simple. All that we need to do is follow the information given here. First, we need to set the structure for the tree diagram. You know, Basically, our company orders from our manufacturer, orders from 3 companies, engines from 3 companies, R, S, and T. So we have 3 branches here. For every company here, so they've talked about they've talked about the engines being faulty, right? Okay, for each of them. But if you're faulty, that means you have the complement, right? Which means not faulty, right? And most of them actually would be not faulty, as we can see. The faulty ones are actually the small percent. So this is what we need to be careful about. We wouldn't actually have only one branch here. So if you have faulty, we also have the complements, not faulty, and it's for each one of these companies. So this is not going to be explicitly stated here that we also have not faulty. So we need to be wary of that by ourselves. Now, I'll first write the probabilities that we found here. So for R it's 0.4, for S it's 0.25, and for T is 0.35. The probability of ordering an engine from them. Okay, or the proportions of engines taken from these companies. Now, if along R, so if you for the engines from company R, 0.02 as a proportion, or 2% of them are faulty, right? So 0.02 as a probability here. And what's going to be the complement? Not faulty. It's basically going to be 1. You know, uh, these two together would be 1. So 1 minus 0.02. Basically, it's the complement, right? So 1 minus your other value. It's going to be 0.98. And I've done the same thing for S, okay, company S, and the same thing for company T by following all these data here. So basically, place the probabilities for faulty here and here, and not faulty is basically the complement, okay, the respective complement. So here this is the complement for this one, this is the complement for this one. Okay, next part, calculate the probability that the engine is from company R and is not faulty. So it's from company R and it's also not faulty. So I'll bring this for reference. I'll bring the tree diagram for reference. Now basically what they're asking is company R. So let's see. In tree diagrams, I find these the most fun when finding probabilities. All that we need to do, unless it's conditional probability, you approach that a bit differently. So all that we need to do to find probabilities here is just go from your starting point to your destination, and you keep multiplying the numbers that you get along the way. That's all that you need to do. Okay, so where are we going? It's company R, so the engine from company R and not faulty. So company R, so we are going to go here, company R, and then not faulty, right? So the numbers along the way are 0.4 and 0.98. That's all that we need to do. Okay, that's all that we need to do. We need to multiply 0.4 and 0.98, and we'll get our probability 0.392. Okay. Now, next part, calculate the probability that the engine is faulty. Again, same approach here. Okay, I'll bring this for reference. We have a few more cases actually. There are a few. So basically, what they're asking us, the engine is faulty. So just the probability of the engine being faulty. Now, there are actually a few ways to approach the faults, the faulty engines here. There are a few ways to get to them. As you can see, there are multiple locations here. So one way is R, you go through R and then faulty, or you go through S and then faulty, or you go through T and then faulty. Okay, so three ways, and in the approach is really more or less the same here. As I've said, in for every way, every path here, you keep multiplying the numbers on the way, and then you need to add the these values for the individual paths. So you have three paths here, as you can see. These are the multiplications of the probabilities on the way, on the way, and you just need to add all of them. All right, so that gives you your final answer of 0.0175. All right, given that the engine is faulty. So given that the engine is faulty, we can already guess that this is a conditional probability problem. Find the probability that the engine did not come from company S. All right, so I'll again bring this for reference. Okay, so what they're asking for, this is important, we need to interpret correctly what they're asking for, is that given that the engine is faulty. So this is given, for given uh, probabilities, we write it like this, a bar here and it's on the right side. Now, given that it's faulty, okay, we need to find the probability that it's not the engine is not from company S, so not S. All right, so uh, the probability of if given that it's faulty, and it not being S, from the engine not being from S, it's going to be, it's the complement, the complement of it being faulty, given that it's faulty and it's coming from S, right? These two are basically complements of each other. That's why this is going to be just 1 minus P, S given faulty, right? P S given faulty. Now, we know the formula for conditional probability. The probability of any event A given any event B is going to be the probability of A and B both happening together, or A intersection B, the probability of that, divided by the probability of your given event. Okay, so this is what we're going to apply here. So this is going to be our A, this is going to be our B, just to use this formula, and this is what we're gonna get. Okay, so one minus that, we're just going to keep it as that for a while. So here what we have is basically, again, A intersection B, basically these two events happening together, so S and faulty, divided by the probability of your given event, so the probability of being faulty. All right, so this is going to be again, that's just as it is. So S and faulty, so S and faulty, we have already seen, actually this was one of the terms, or portions of the previous part, but again we can, if you want, we can just find this. So S and faulty, right? So we can just need to traverse a tree diagram. There's only one way to do that. S and then you go to faulty, so 0.05 multiplied by 0.01. Okay, so this is basically how we get 0.025, just the multiplication of those two. Okay, and divided by the probability of being faulty, we found that in the previous part, 0.0175. Now this is going to, we have everything in terms of numbers. This is going to give us our answer of 6/7. Okay, the value is 6/7. All right. Question number 4. A discrete random variable x has probability function. Okay, the probability of x being small x, so a particular value is going to be okay. So if x is either 0 or 1, this is basically how the function looks. Okay, if x equals 2 or 3, this is basically how the function looks. This is what we need to use. If x equals 4, we just need to plug the value here, and any other value of x, the probability is going to be 0. Where k is a constant, so show that k equals 1 by 9. Okay, Now, what do we know about okay, first thing, I'll actually evaluate, or at least simplify the expressions here, for the probabilities. So for x equals 0 and 1, all that we need to do to find the probability here, or at least the expression for that, is plug it into this formula right here, right? K into 2 minus x, right? So here it's k into 2 minus 0, that's 2k. K equals 2 minus 1, that's k into 1, so 1k, just k. Uh, for 2 and 3, we just need to plug in this formula. So k into 3 minus 2, that's just k. For x equals 3, it's k into 3 minus 3, that's 0. That's 0. And for x equals 4, we just need to put in this formula. So k into 4 plus 1, that's 5k. That's 5k. And any other values, obviously, we are not writing any other x values because the probabilities for all of them are 0, so there's no point in writing them. Okay. Suppose say if you even if you wanted to add something like equals 5 here, obviously the probability of that is going to be 0. It's basically useless. So that's why you're not writing that. Okay, now as we know, the sum, as we have been using quite a few times, the sum of all the probabilities of any event, any distribution, is going to be 1. So sum of all of these, if you take the sum of all of these, probabilities that we have found, it's going to be equal to 1. And basically, if you add all of them, it's going to be 9k here, and 9k is equal to 1. K is equal to 1 by 9. So we've basically shown what they asked us to. Okay. Now, next part. Find the exact value of, so B is the probability that X is greater than or equal to 1 and less than 4. So I'll bring the table for reference again. Now, and here I've actually put the value of K here so you can numerically see all the probabilities. So, as you can see, X can be 0, 1, 2, 3, or 4. So x, capital X being, greater than or equal to 1 and less than or equal to 4. What does that mean? Okay, so x can take on certain number of values. So it cannot take on 1. That's not greater than or equal to 0. Can take on 1. Can take on 2. Can take on 3. It's still less than 4. Cannot actually take on. Okay, so it cannot, as I've said, it cannot take on 4 because it's, they said strictly less than 4. Okay. Again, I'm actually ruining things here a bit. Can I go back? No. Doesn't seem like it. So no, as I've said, it's we don't have a less than or equal to sign here, so you cannot actually include 4 right here. So this is going to be, so our possible values for x, that x can take are 1, 2, and 3. Okay, all that we need to do is actually just add the corresponding probabilities. So going to be probability of x equal 1, x equals 2, and x equals 3. And okay, I didn't mention this a while ago. This is actually shorthand. This in small p, and then writing any x value. There's actually shorthand for writing p, capital X equals x. Just shorthand. Okay. Now all that we need to do is add in the probabilities for the allowed values, and what we get is 1 by 9 plus 1 by 9 plus 0, going to give us 2 by 9. Next question is, E of x. So basically the expected value or the mean of x. Okay. The formula for that is the expected value of x is going to be equal to the sum of x into the corresponding probability. So you take x, an x value, you take the probability, you multiply them, you do this for every column, and then you add all of them, add all the values. So that's going to be your expected value or your mean of x. And so this is what I've done here. Took every, for every column, I took the x value, multiplied by the probability, did this for every column, and then I just added all of them. As you can see here. All right. This is going to give us a value of 23 over 9. So that is the exact value of the expected value of x. Okay. All right. Next part. The expected value of x squared. This is really the same. Okay, any expected value actually takes on the same format, except you need to be careful. What's here. It's x squared. That's why you place the square here with the x. Okay, so basically you take every, you take the probability, and if you take x squared, okay, multiply these two, add all of them, for every, for all the columns, and then you get your result. Here, as you can see, this is what I've done. And this is, every x value, as you can see, it's squared, okay, and then you get your answer of 85 over 9. All right. So last part, the variance of 3x plus 1. Now here I'll already discuss, what we should, go towards, because in any problem, what we should do is first, see what we need to get. Okay. Uh, See and remember what information we have on hand, and basically fix a course of action. Okay. How do we get, from what we have to our goal? Okay. So it really doesn't help to blindly go about any math problem. So it doesn't usually result in productivity. So let's see what we need to do. So we have the expected value of x squared, and we have the expected value of x. With using those, we can actually find the variance of x. So you can actually find the variance of x here, and it's going to be, as you can see, you just plug the values. It's going to be 236 by 81. Anyways, what should we do? Okay, we have the variance. We need to find the variance of 3x plus 1, not x. And the thing is, when you have the variance of a variable, okay, the variance of a linear expression of that variable, it's very easy to find. Okay, it's very easy to find. We need this, and we actually have a formula for the variance of any linear expression of that variable. It's going to, the variance of ax plus b in general, where a and b are constants, is going to be a squared. A is basically the coefficient of x. A squared multiplied by variance of x. As you can see here, b doesn't really affect anything. It's because, uh, changing the position of all values doesn't really affect the variance of the spread. All right. Anyways, this is the formula. We are just going to apply it here. So a here, as you can see, it's the coefficient of x, that's 3. So what we're going to have is a squared, so basically 3 squared multiplied by variance of x. We have all the values, so this is 9, this is equal to, variance of x, as we just found, is equal to 36. 236 divided by 81, and we get 236 divided by 9. Okay, so we're doing question number 5 now. The weights in grams of a random sample of 48 broad beans are summarized in the table. So this is basically a table, and this is how you interpret this. So from 0.9 to 1.1 grams. In this range, you have nine broad beans. So 9 broad beans have a weight between 0.9 and 1.1 grams. Okay, and this is how you interpret the whole table basically. And these are the midpoints of every class. So basically, suppose say this class, if you take this class, the midpoint is basically the mean of the first and last values. Well, here it's actually here you can do that, because there's actually no gaps between the first, this value and this value and stuff like that. If there were actually gaps between the intervals here, we'd have to do something a bit different. Okay, but here we don't need to worry about that, and especially because they gave the midpoint, so we definitely don't need to worry about how to calculate that. So I was just explaining what the midpoints mean. So it's basically here it's just the mean, it's just the average of first and last value of you know of each of these intervals. It's very aptly called midpoint. As you can see, it's right at the middle of the right in the middle of the interval. It's going to be, as you can see, it's going to be 1.0. So basically the same thing here. So the midpoints, we are going to use them, as we'll see. First thing though is that 48, as you can see, it's the sum of all the frequencies. Okay, 48 broad beans, it's the data for all of them. This is obviously going to be the sum of all the frequencies. Okay, or you might also call that n. Okay, which basically the the total number of items. All right. So, and we may use, okay, so you may assume that the sum of f multiplied by y squared. So I know every frequency multiplied by y is the midpoint, the class midpoints here. Okay, so frequency multiplied by y squared. So the sum of all of them is equal to 101.56. A histogram was drawn to represent these data. the 2.1 is less than x to less than or equal to 2.7, and it's kind of like a long way of saying this. So from now I'll just say 2.1 to 2.7. Okay, the 2.1 to 2.7 class was represented by a bar of width 1.5 centimeter and height 1.1 centimeter. So we're drawing a histogram, and for this interval the width and height was this 1.5 and 1 centimeter respectively. Find the width and height of the 0.9 to 1.1 class. So just given the data for this one, we need to find the data for this bar. Okay, 0.9 to 1.1. Okay, how do you go about that? One thing we need to realize, first thing to find the width, is that the bar width, the width of the histogram bar, okay, it's just going to be a scaled up version of the class width. Okay, so the histogram bar is always going to be proportional to the class width. Okay, so the what here the class width, the class width is basically the length of the interval. Okay, the length of the mathematical intervals here. So 2.7 minus 2.1 is basically 0.6, and the bar width is basically what you see in the histogram. Okay, and that you can draw it in any way, like if you have a different scaling factor, you can make it bigger, you can make it smaller. This is obviously not going to change, or I mean at least for a particular interval. You cannot actually just change it if you wish. All right, anyways, so I hope what in the bar width and the class width are clear. It's just concerned with the interval itself, and this is basically the physical representation on a histogram. All right, so the bar width is going to be proportional to class width, and we have this data for this class. Okay, the this is the bar width, this is the class width, and here what we have is the class width. Okay, for the one that we the for the class that we're concerned with, we only have the class width. But well, since we know we have that bar width is proportional to class width, okay, and we have the data for one set, you could say one data set. Okay, uh and we have one value for in the other. Given that we have a proportionality relationship, direct proportionality, we can definitely find the unknown value. Okay, so here's what we'll do. What happens in direct proportionality? If some value y1, not y, sorry, if not y1, if some value y, is let's see, if some value y is proportional to x, okay, it's proportional to x. What happens? The ratio of any of a value of y with a corresponding value of x, okay, a corresponding value of x is equal to, is going to be the same as the ratio of another the ratio of y with a value of x, the corresponding values of y and x for some other pair. Okay, you're going to choose some other pair, and if you again calculate this ratio y by x, it's going to be the same. All right, this is what direct proportionality implies. We are going to use that here actually. So suppose say the bar width that we want to calculate, suppose I call that bar width v dot w dot. Anyways, so the bar width that we want to calculate divided by the corresponding class width. Okay, this one, this is the one, the interval that we're concerned with, is going to be equal to, we take any other pair, okay, and calculate the same ratio. So we actually have information here, the bar width for, so we have information for this class 2.1 to 2.7. okay, the bar width is 1.5 centimeters, and the class width is 0.6. It's just 0.6. Now we can multiply both sides by 0.2 and we'll have our answer. So this is basically what I did here. The bar width is going to be 0.2, 0.2 by 0.6 times 1.5. Just a rearranged version of this, and we get the answer of 0.5 centimeter. Now to find the height on the Venn diagram, we need to remember the fundamental property or feature of a Venn diagram, and that is that for every bar, and even for the whole histogram itself, or any portion of it, the frequency, okay, is going to be proportional to the histogram area. Basically, it's going to be proportional to the histogram area. One way to write that is, the frequency is going to be k multiplied by the area. Okay? Or one way you can write, as an equation, you can write f equals k multiplied by width into height. Okay, so we have the information for one class, for this class, the width and the height. Here we're actually just going to use the width and height of the histogram. Okay, so for the 2.1 to 2.7 class, which you have information for, what's the frequency? We are going to apply this formula. What's the frequency? Let's say it's equal to 2. It's equal to 2. That's going to be equal to k, some constant k, we don't know that yet, multiplied by 1 point. Okay, so the width and the height, the product of the width and the height, so 1.5 and 1. Okay. And from here we have an equation. You can find k from here, and we do the same thing. We do the same thing for the class that we're concerned with. For this one, what's our frequency? It's 9, right? 0.9 to 1.1. It's 9 is equal to k. We already have the value of k, multiplied by the width into the height. So the width we already have, the height is what we need to find, and here we will get our height. It's 13.5. Need to be careful that we put the correct unit. Okay, it's going to be the same as all the physical length dimensions here, so it's centimeters. All right. One last thing I'd like to mention is, interestingly, you might think that, okay, so we use this relationship for proportionality before. Why are we bothering with going to the old one, or another version? You could actually use this for this problem also. You'd actually get your answer much more simply. Okay, so suppose, say, for this one, it's basically frequency by area is equal to another frequency by area for another pair. So suppose say we take this class. We take this class. Okay, the frequency is what? 2 divided by the area. It's basically in width into height, so 1.5 into 1, it's basically 1.5, going to be the same as it's going to be equal to the frequency. Okay, for this class, it's going to be, okay, the frequency is 9, as we found, 9 divided by the area. The area is what? 0.5. We have the width, we don't have the height, that's the unknown. So 0.5 into h, so that's the area, and from here we can easily find h. Okay, so that's another way to do that. You should do what you're more comfortable or convenient with. So let's move on to the next part. Okay, so the table here is for reference. So we're moving on to part B. So the table again is just for reference. Okay, give a reason to justify the use of a histogram to represent these data. Now we can see this tabular data. In this tabular data, we have these intervals, right? We have these intervals. Okay, it's not like just at 0.9, then you have the frequency for that. You have 1.5, the frequency for that. No, you have ranges. You have intervals. Okay, and this is and we don't precisely know where all the 48 values are, right? They're included in the ranges. We have the frequencies. Okay, we don't know the exact values. So this data, as you can see, since it deals with intervals, it's actually continuous data. Okay, the data is continuous, and any data that's continuous, it's actually fit for a histogram. Okay, all right. A discrete data you cannot represent with a histogram. It has to be continuous. It has to be continuous. All right. Next, part C. Estimate the mean and the standard deviation of the weights of these broad beams. Okay. So we need to find the mean and the standard deviation. So the formula for the mean, x bar. So the weight here is x. So x bar, the formula for that is basically the total divided by the number of items. So how do we find the total? To be honest, for this type of continuous data, where the values aren't exactly known, we cannot actually exactly find the total. We need to estimate that as uh, every total right here. For every row, we need to estimate that as the frequency. Okay, how many times it occurs, multiplied by the midpoint. Okay, multiplied by the midpoint. So that's what's being done here, f into y, and then you add all of them. For all the rows, you add all of them. Why we're doing this is, it's reasonable to think that, it's just an estimate. It's just, we can only estimate. So that's why we're thinking that it's reasonable to think that on average you could say that the values in a certain interval, just as an average, you could say that it's going to be close to the midpoint. So that's what the underlying assumption here. Okay, so that's how you estimate the total and divide by the total number of items of the sum of all the frequencies. This is basically, okay, first sum of the frequencies is 48. Okay, then you need to find the sum you need to find the sum of f multiplied by y. Okay, so here's what I've done. So f multiplied by, every frequency multiplied by every midpoint in the corresponding midpoint, and then you just add all of them up. Then you just add all of them up for all the rows. Okay, so we have 1 2 3 4 5 6 7. Yes, same as the number of rows, and this is going to give us an answer of 1.4125 grams. All right. um, we also need to find the standard deviation. First, I'll actually start off with the formula for the variance. So basically, sigma squared. Okay, the formula is sigma squared equals the sum of frequency multiplied by y squared. Okay, I already explained what that means. Divided by the sum of the frequencies, basically the total number of items, minus the square of the mean of x. And this is how I actually like to remember the formula, is that your variance, okay, your variance sigma squared is equal to the mean of the squares. Okay, right, this is basically the mean of the squares. You take the sum of all the squares, okay, and you take their mean, so basically divide by the total number of items minus the square of the mean. So you have the mean, you square that, and then you subtract that from here. So this is how I remember the formula. But anyways, we need to find the standard deviation, which is sigma. It's not sigma squared. So first we need to plug in all the values. We actually have, they allowed us to use this sum of f into y squared. It's going to be 101.56. Total number of items we know is 48. We already found the value of x bar. Okay, then you also need to take a square root. Need to be very careful about this, that we need to take the square root at the end, and this is going to give us a value of 0.357 grams. Right. Okay, next part. Use linear interpolation to estimate the median of the weights. Now we need to find the median, or to estimate the median, and this is going to be by interpolation. Okay. So first, where is the median going to be located? And it's the same thing as we did, a while back in a certain question in this paper. So the median is going to be halfway across the whole data. So you have 48 data points in total. Median is going to be just 2 by 4, or 1 by 2, or just halfway, multiplied by 48. Okay, so this is going to be your 24th weight, and here it's not discrete data, that's why you're not going to round up or anything. Okay, we just need to take this value as the position. All right, which lies in the 1.32. Okay, so here actually I'll use this table as reference. Okay, so where does the 24th value lie? But between 0.9 and 1.1 we have 9 values, and if we go up to 1.3 we have 12 more. So 9 plus 12, that's 21. And then in this class we have 11, the next 11 values, and that's definitely going to include the 24th value, since up to this much we covered, let's say 21 values. The 24th value is definitely going to be here. All right, that's why the median is in this class. So this is important for the interpolation. We need this class, values of this class. So interpolation, we first will I'll first draw this diagram. Here it's basically the class endpoints. In somewhere you'll have Q2. So Q2 is in the 24th position. The first point of the class, okay, the first value is going to be the 21st position. How do we find that? It's basically the cumulative, the total frequency of all the classes that came before that class, okay, before this class. And this value right here is basically the sum of all the frequencies, okay, until this class. So even this one added together. So that's how we got the 32. Now what I need to explain is the main principle behind interpolation. That is that, okay, first I'll actually bring this out, so I can explain it better, like this, is that corresponding ratios, we can take corresponding ratios and they're going to be equal. Okay, suppose, say, this is what I mean. On this side, you can say on the values or weights side, if you take this distance right here, this difference or this length, and divide by the same corresponding value here, divide by the same, it's on the other side, it's dealing with frequencies, but still it's the corresponding value here. And this is the principle behind interpolation, is that we assume, okay, that they're similar or really approximate the same. Okay, that's basically how we estimate. So this difference, Q2 minus 1.3, divided by this distance, 24 minus 21, going to be the same as if you take any other plausible ratio. The one that I like to do is the whole thing here, because you don't introduce any more unknowns if you do this. So the whole here divided by the whole here, okay, that's going to basically, this is going to be basically equal to that. So 1.5 minus 1.3 divided by 32 minus 1, so minus 21. I have an equation involving only Q2, and we can find the Q2 from here. So it's going to be 1.35 grams correct to 3 significant values. All right. Part E. Estimate the probability that its weight lies between 1.1 grams and 1.6 grams. All right. Now, the estimated number of broad beans in between the limits that they're saying is, let's see, we need to estimate. It's going to be this. How am I finding this? We basically need to take, the sum of all the frequencies. Okay, we need to add up all the frequencies beginning from 1.1 and ending at exactly 1.6. We cannot, even if either of the points is kind of like a middle of a class, we actually, we need to scale it accordingly. We cannot take the whole class. This is what I mean. I'll just show in a bit. So from 1.1 you can go up to 1.3 first, and then you have 12 data points there. Then from 1.3 you can go up to 1.5, and you have 11 more data points there. However, when you go from 1.5, so here you actually have to end at 1.6, so no choice. 1.5 to 1.6, that the whole frequency of this class is actually not going to be counted. Okay, it's going to be counted in proportion to how much length we're taking. Basically 1.5, 1.6 minus 1.5 is basically 0.1, 0.1, and the width of the whole class is 0.2, right? 0.2. Okay, so the proportion that the proportion of the whole class that you're taking is actually 0.1 by 0.2. It's basically half, right? It's basically half. So that's why we need to multiply that by scale that by scale the frequency by this factor right here. Okay, so that's what I did here, and we'll get that. Okay, so this is the reason, and we'll see that the estimated number of broad beams in this interval is 27. All right, now we're not done yet. We need to find the probability. Okay, the required probability is going to be basically, as we know, the required number of items. Basically, this is the required items, right? The broad beans in this range. So the number of required items divided by the number of total items or frequency. That's how business works. Okay, that's how probability works. Okay, so that's basically what we're doing here. 27. Your required number of items. All right, so this is, as we know, basic probability definition. That's what we are applying here. So the required number of items, basically the items that meet your criteria. This was our criteria. This is the number of items that meet our criteria divided by the total number of items. That's, as we know, it's 48. Right here. So that gives us an exact answer of 9/16. Okay. All right. Next question. One of these broad beans is having a recorded weight of 0.95 grams was incorrectly weighed. Okay. The correct weight is 1.4 grams. State, giving a reason, the effect this would have on your answers to part C. Part C is where we calculate the mean and the standard deviation. Do not carry out any further calculations. So we cannot rely on calculations, just need to rely on logic, statistical logic. Now, the corrected value, this value that we got after the correction, is actually more than 0.95, right? It's more than 0.95. So this definitely causes f multiplied by y, basically frequency basically your estimated total, right? That we used to calculate the mean. It's definitely going to be higher. Okay, one of the values are higher. It's definitely going to be higher. If that's the case, our mean definitely has to increase. All right. Also, what about the standard deviation? Well, 1.4 is actually closer to the mean than 0.95. Okay, so the mean, as we saw before, it was 1.4125. So 1.4 is definitely closer to that than 0.95. So what happened here? Basically, this was our old value, but this was changed to this. Now the changed value is closer to the mean than what it previously was. Okay, so being closer, values being closer or more concentrated, in the area, in the region of the mean, basically means that your spread is low. Okay, and if the values move away, that means your spread will increase. So here one value actually came closer to the mean than it was before. So data as a whole, even by a small margin or percentage, it's going to be more concentrated around the mean. Okay, that's why the standard deviation decreases. The spread is lower, the standard deviation is going. All right. Next, let's move to question number 6. So, the waiting time L minutes to see a doctor at a healthcare center is normal distributed. Normal distributed with L, it's the distribution is it's a normal distribution with a mean of mu and a standard deviation of sigma, a variance of sigma squared. That's why you have the square there. Okay, given that the probability of L being less than 15 is equal to 0.9 and the probability of L less than 5 is equal to 0.05. Okay. Part A asks us to find the value of mu and the value of sigma. All right. So first of all, um, we have the probability of L less than 15 is equal to 0.9. That's given. Okay, but we cannot just work with any normal distribution that's given to us with any possible mean and standard deviation. We can only work with the values of the standard normal distribution. That's why we need to convert this value to the corresponding value for the standard normal distribution. And to do that, we'll use this conversion formula. So the corresponding z value is going to be, the corresponding value of this variable, okay, what we want to convert, minus the mean, okay, the mean of the variable divided by the standard deviation. All right, so if we do that, mu and sigma here are actually, mu and sigma here too. So those are same names as the unknowns here. And, the value that we are converting is 15. So that's why you have this 15 here. So this, the probability of L being less than 15 is equivalent to the probability of Z, the standard normal distribution variable, being less than this converted value. Okay, 15 minus mu divided by sigma. And this is equal to 0.9. Now, this is where, and actually for both of these, we need to be cautious of something. We need to, be aware of something. Is that both of these 0.9 and 0.05, they're kind of like neat values. Okay, they're not very long decimals. Or what I mean is I think that's really the only way I can say this. I'm not sure how else to say this, but they're kind of like neat values. Okay, neat values. It's not like something like 0.6442. Okay, not something like that. So, and when you have these sort of neat values, you're likely going to have to use the small table, which has the values for, the values in the small table are for this. So p z greater than a is equal to some probability. So some probability small p. So given that you have the small p, and given it's a neat value, you should be able to find this value right here. Okay, if you bring your left hand side to this form, p z greater than something, you should be able to find that something from the small table. So that's what the small table is used for. So the neat values, that was what I was saying. The neat values, you'll find them in the small table. But before that, as I've shown here, first we need to convert the z expression here to z is greater than something. Okay, you cannot have less than as you have here. Okay, to do that, we will use a certain formula, and it's actually something that you can easily make out using common sense or a diagram. Is p z less than a is obviously going to be 1 minus p z greater than a, because being less than something and being greater than something, these are complements. Okay, they're complements, they're total probability. Less than something, z less than something, and the probability of that, and pz greater than something, they're complements. Okay, they're complements. Okay, and their total probability is going to be 1, and that's why you can find 1 if you subtract the other from 1. Okay, so using this, we can actually have z greater than something here. P z less than 15 minus mu by sigma. It's the same thing as 1 minus p z greater than that value. It's going to be equal to 0.9. The right hand side is unchanged. And then what do we have is p z greater than 15 minus mu by sigma. If we make that the subject, it's going to be 1 minus 0.9. That's 0.1. So if we see the small table, we'll see that for 0.1 the value of z is 1.2816. Okay, so it was necessary that this was greater than for us to use the small table. Okay, otherwise we couldn't have actually written this. All right. So if that's the case, we can actually just simplify this a bit if we do some algebra. So we get an equation in mu and sigma. So mu plus 1.2816 sigma is equal to 15. This is our equation 1. All right. Now we have another piece of information that p in the probability of L less than 5 is equal to 0.05. Again, another need value. So again, we'd probably have to use the small table. L less than 5. It's the same thing. We are again using the conversion formula. So it's the same thing as P z less than 5 minus mu by sigma, and it's going to be equal to 0.05. Okay. Now we can actually use the symmetry of the standard normal distribution here. So, and this is something that only works if you have a standard normal distribution. Well, all normal distributions are symmetric, but here what's special is that the mean is 0, so that's why here this thing actually works. Okay, so suppose say you have some value a, or actually let's say this is negative a. Let's say this is a. Okay, so due to the symmetry, this is a standard normal distribution. Okay, so see here, this area and this area need to be the same, and these two are probabilities, so these two probabilities are the same. This probability is pz less than negative a, this probability is pz greater than a. So pz less than negative a, pz less than negative a is equal to pz greater than a. You can just do this by seeing the diagram every time. Now one thing you might ask is, my formula that I wrote here looks a bit different from that. Well, here all that you need to do is put in negative a instead of a. Okay, if you put in negative a instead of a, you'll actually get this. So what you're gonna get is pz less than negative of negative a, that's going to be positive a, and it's going to be here. You're again swapping a by negative a, so you're gonna get negative a here. Okay, that's how this comes. But anyways, the main thing is that we can see that this is correct, that pz less than some value is equal to pz greater than the negative of that value. Okay, the negative of that value, it's flipped over 0 here. That's what matters. All right, now if we use that, we see that p z less than this is equal to 0.05. So pz greater than the flipped over version, the negative of this value, okay, is going to be equal to 0.05. Now why did I do this? Because I should have actually stated that before. We again, this is a need value, so we are probably going to have to use the small table. But to do that, we cannot actually have z less than something. We need the expression to be z greater than something. That's why we had to convert it to z greater than something before using the small table. So from the small table, what we get is the corresponding value for 0.05 is 1.6449. Okay, and from here we can find another equation in mu and sigma. So mu minus 1.6449 sigma is equal to 5. All right, this is our equation 2. Now using these two, we can actually solve for mu and sigma. So we have two unknowns and two equations. We should be able to solve for them. All right, so for that, what I'll do is actually use elimination. We have mu here, mu here. If I subtract equation 2 equation 1, the mu's cancel out, and what I get is 1.2816 sigma plus 1.6449 sigma. That's 0.9265 sigma. This is going to be equal to 15 minus 5. So 15 minus 5 is 10. Right. So from this we can actually find the value of sigma, which is 3.42 if we round that to three significant figures. And using that in any one of the equations, I'll substitute that in equation 1. We get the value of mu. So mu is equal to 15 minus, you bring this to the other side. So minus 1.2816 multiplied by sigma, which is sigma is 3.42, is equal to 10.6. Now here's something that I'd like to note, and this we'll see in the next slide too. But suppose that this value and this value, we should be actually saving these in our calculator, in the variables in our calculator. Okay, because the more we use them to do further calculations, if we use the rounded values, the more our error becomes. That's why we should use the exact value, save them in the calculator and use those. Okay, even if we write it like this, we should actually in our calculator we should use the exact values, okay, that are saved in the calculator. All right, so moving on, there are 23 people waiting to see a doctor at the healthcare. Determine the expected number of these people who will have a waiting time of more than 12 minutes. So L was our waiting time. More than 12 minutes, that basically means L being greater than 12. Okay, so basically determine the expected number of these people for whom the L is greater than 12. Correct. Now, first we need to find the probability of L is greater than 12. Okay, and then, okay, so this is the plan. The probability here, you can actually treat it as a proportion. Okay, when you're dealing with how many people there would be from a sample, probabilities, you can actually treat them as a proportion. Okay, so first we'll find the probability, and using that proportion slash probability, we're going to find the expected number of people out of the total of 23. Out of the total of 23. All right, so P, the probability of L being greater than 12, again we convert, and now we have both the value of mu and sigma. We know them, so we're going to get a numerical value here. Now this is what I just said a while ago, is that we should be using the exact values of mu and sigma. All right, if we do that, we get 0.4. Pz is greater than 0.4. Now that's the same thing as 1 minus pz being less than 0.4. Okay, one thing I'd like to note is, just to not create confusion, you might think that this is a neat value, but the thing is, the small table is only for, you have, what's the small table for? It's only for when you have a value of p, some neat value of the probability, and from that you convert to a z value. Okay, you find the corresponding z value. It's not for the other way around. The large table you can actually use for both. Okay, but the small table you can actually not do this the other way around. Okay, so now you might think, so why not use the large table every time? Well, for this one purpose, where you have a need value for the probability and you want to convert it to the corresponding z value, using the small table obviously has a much higher accuracy. That's why you use it when we can. All right, now the probability of z being greater than 0.4, as I discussed, being greater than something and being less than something, they're complements. So this is equal to 1 minus pz less than 0.4. And for 0.4, from the large table, we find that the corresponding value of the probability is 0.6554. Okay. For the large table, it's important that we have less than, z less than something. All right. Now, what we get here is 0.3446. All right. So now let's assume, okay, let the expected number of people with waiting time more than 12 minutes, let that be x. Okay, so now what do we know from the basic definition of probability or even proportion is that probability is equal to your number of items that meet the criteria. Okay, here our criteria is waiting time being more than 12 minutes, people with waiting time more than 12 minutes. Okay, so that we assume that that it's x. So our a number of items that meet the criteria, that exactly x. Okay, that's exactly x. All right, divided by your total, okay, your whole sample size. Okay, so the total number of people that you're considering is 23, so that's why you have 23 at the bottom. Now we can easily find x, which is what we need to find as the answer for this question. X is equal to okay, that came up a bit late. So as I was saying, is probability is the number of items matching the criteria divided by the total number of items. All right, now from here what we get, x is equal to 23 multiplied by 0.3446, what we just found a while ago, and what we get is 7.9258. Okay, fair enough. We got a value, but the thing is that this is actually a certain number of people, right? A certain number of people, and you obviously cannot have decimal number of people, so we need to round that to the nearest whole number. Okay, so we will get 8 here. So there are 8 people. There are the expected number of people is 8 who will have a waiting time of more than 12 minutes. All right. Okay. Last question, question number 7. Events A and B are such that the probability of A is 0.5, the probability of A given B, given that B happens, the probability that A also happens is two-thirds, and the probability of A prime union B prime. So the probability of either A not happening or A prime happening, and B prime happening. Okay, either both of them or either of them. So that probability, the probability of their union is 0.6. So the first question is find the probability of B. Now we're given quite some information. We need to find the probability of B. Okay, so first let's actually think about how we should solve this problem. Okay, so here what I have is the probability of A given B. We have the value for that. We need the value for this. Okay, and in this formula I wrote this formula. This is a conditional probability formula, as we all know. However, we don't actually have P A intersection B. But we can actually find it from here. We can actually find it from here. And that should allow us to find the value of the probability of B. Let's continue down that track. Okay. So the probability of B, if we just rearrange this, is going to be the probability of A intersection B. Still don't have that. That's why that's marked in red. Divided by the probability of A given B. Okay, we have that. Okay, so at the end we can just substitute the value. All right. Now this diagram is just for reference for this statement. The probability of A intersection B, this red area, is just going to be 1. Okay, the probability of the whole universal set minus the probability of everything that's outside this red area. And what's outside this red area? It's basically A prime intersection B prime, right? Everything outside A intersection, the union of that with everything outside B. That's basically this blue area right here. So these two are complements. Okay, so now we can easily find the value of A intersection B because we know this value. Okay, this is 0.6 as given, and now the probability of A intersection B is 0.4. Okay, so now we can easily just plug in this value and this value, and we should be able to find the probability of B. Probability of B is 0.4, that's A intersection B, divided by the probability of A given B, that's 2/3. Okay, that gives us an answer of 0.6. All right, let's move on to part B. Find the probability of A prime given B prime. Given that B prime happens, find the probability that A prime happens. All right, and the major realization here is A prime and B prime are themselves events. So any formula that we can apply to any two events, we can also apply to these. Okay, because these are just some events. Okay, so the probability of A prime given B prime is equal to, this is what I was saying, we have the conditional probability formula. Okay, but that it's usually written as we saw just a while ago, A given B is equal to the probability of A intersection B divided by probability of the given event, which is B. But then again, the A prime and B prime, they're again just some events. We just need to treat them as some events. Okay, so you just need to replace all of these by A prime and B prime accordingly. So A prime given B prime is going to be A prime, this event intersection the other event, divided by the probability of the given event, which is B prime. All right, now both of these are red marked because we don't have any of them yet. Okay, however, we can actually find one of them pretty quickly. The probability of B prime is just B prime and B are complements, so it's going to be 1 minus probability of B. We have the probability of B from the previous question, that was 0.6. This is going to be 0.4. Now, why did I find the probability of A prime here? It's going to be 1 minus probability of A, and that's 0.5. We'll see that in a bit. We actually need that. So now all that we have left to do is find the probability of A prime intersection B prime. And for that, we are actually going to rely on the union intersection formula, the relationship between them. So the probability of A prime union B prime is equal to the probability of A prime, okay, plus probability of B prime minus the probability of A prime intersection B. This is basically just your formula. Your formula is normally written as this: A union B is equal to the probability of A plus probability of B. Basically, sum of the probabilities of your two events minus the probability of the intersection. Probability of intersection. Now we have A prime and B prime as the events, so we're just using them instead of A and B. Nothing more. All right. Now we actually need this. Okay, we need this here. Okay, and we actually have all of these, right? We have all of these values. If we plug them in, we can actually find the value of B A prime intersection. First, I just rearrange this a bit to make this the subject. Okay. Now we have all these values. Probability of A prime is 0.5. The probability of B prime is 0.4. Probability of A prime intersection B union B prime that was given in the previous slide. It was 0.6. Okay. So minus 0.6. This gives us an answer of 0.3. Now we have all the values that we need to plug in. We'll plug them in here, and then we'll get an answer of 3 by 4. 3 by 4. 3 by 0.4, that's 3 by 4. All right. The event C has the probability of C is 0.15. A and C are mutually exclusive. A and C are mutually. The events B and C are independent. Now, what does mutually exclusive A and C as? We'll see that in the next slide when we draw the Venn diagram. That's the next question. But obviously, to do that, we need to know what's mutually exclusive. Two events are mutually exclusive when they cannot happen together. It's impossible for them to happen together. Okay, and on a mathematically, you could say the probability of their intersection of them happening together is 0. On a Venn diagram, what you see, since the probability of the intersection is 0, you don't see any intersection. Okay, you don't see any intersection. So these two don't intersect. And even on the off chance, if you see on some diagrams that if suppose say you wanted to represent two exclusive like this, okay, and you do them like this, so what do? Instead of erasing this, you like to still be able to use this diagram, but still carry on. Well, you can just put a zero here. Okay, that still means the same thing, that they actually probability of them happening together is actually 0. All right. Now what they're asking us is find the probability of B intersection C. But that actually B and C are independent. This information is actually likely to be more useful than that one. Okay. What does being independent mean? What does being independent mean? There are quite a few interpretations for that, and quite a few results that come about from that. But one of those is that the probability of the intersection B intersection C, okay, is just equal to the product of their individual probabilities. Okay, that is one of the features of independent event. And from this, we can very easily find the probability of B intersection C. Okay, it's just the product of the individual probability. So we actually have probability of B and also probability of C, which is given here. 0.6 probability of B multiplied by 0.15, which is probability of C. This gives us an answer of 0.090. All right, and this should be the last part of this paper. Draw a Venn diagram to illustrate the events A, B, and C and the probabilities for each region. Now, there is one thing that I'd like to clarify here. Why I've drawn this. Normally, if you have 3 events, the most general way that you can draw them, is like this. Okay, is like this. Now, why did I draw them like this? Because they've already told us that A and C are mutually exclusive. Okay, that's why these two are going to be apart from each other. They won't have an intersection. You could actually draw it like this, but on some parts you're going to have a bunch of zeros. So that's why rather than going to that effort, I just view them separate from the get-go. Okay, and B has shares in both of them, as you can see. So it was not said that B is exclusive from either one of them. So that's why it's possible for it to have properties here, and it actually does, as we'll see. So let's actually fill in all these values. Okay, one thing is P A intersection B 0.4. We actually found this before. We're just plugging it in.
If that's the case, and we also know that the probability of A is 0.5, right? The probability of A is 0.5. The whole thing right here is 0.5. That's the case, we can find the probability of this part. 0.5, this whole thing minus, this portion, 0.4. Well, obviously this is not to scale. Okay, this gives us a value of 0.1, 0.1. Okay, also we know, we just the last part, just the previous part, we saw, we found the probability of B intersection C. That came out to be 0.09. Okay, and we know the value of the probability of C, the whole thing. Okay, the whole thing is 0.15 as they had written. So we can easily find the probability of this portion. Okay, this kind of like a portion of the moon, you could kind of like a face of the moon. This portion we can find the probability pretty easily. All right, so it's going to be the whole thing minus the probability of this portion. Again, not to scale. It's going to give us 0.06. All that we have left is this portion and actually this outside portion, outside all the sets. Okay, this portion, we actually know the probability of B, right? We know the probability of B.
Follow us on social media: Facebook, YouTube, Twitter, Snapchat, Instagram, and LinkedIn. So, don't be late. Enroll to your desired courses and let Bizuz be the guide to your dream grades.